So I'll just take a picture of myself. Grüezi all. My name is Pim. I've been a member of the RIPE community up north for a little bit, about 26 years or so. As Yazid said, I started in the Netherlands as a network engineer. In 2006, I moved to Switzerland. In the pandemic, I got kind of bored a little bit and incorporated a tiny company called IPNG Networks in Switzerland. You may not recognize the top map. Nobody does in Europe either. That's where I live, a small network that I built over there around the Zurich metro area. The bottom graph you may recognize, we run 14 completely open source based off of Debian software routers in Europe, from Zurich to Frankfurt and then up to Amsterdam. The north of France called Lille, and then Paris and Geneva. So technically we appear on the flap, except the L here is not London. We have a bunch of BGP adjacencies, about 2,200 or so, and we acquired a 4-digit AS number for vanity purposes from that 6-access project that was mentioned before. Before I continue, I come from Switzerland, where people obsess about time. I have a 30-minute slot, and I stand between you and tea or whiskey. I'm partial actually to both beverages myself, but I am going to run late so that, maybe 10 minutes past or quarter past the hour, just to make sure that when I come back to Switzerland, I don't get arrested for being late. Actually, I also like Tofinos and Bluefield DPUs, but what if you didn't have all that stuff and you just used the Linux kernel for routing? It's actually quite slow, notoriously. Like, all these decisions have to be made for each individual packet, and we do in a large flow many packets per second. And so imagine that your kernel, as you're watching a YouTube cat video, needs to get interrupted, or maybe for a couple of packets gets interrupted, and then needs to make a decision what to do with this packet. Is it Ethernet? Is it firewalled? Should I NAT it? Should I forward it to another host, or should I terminate it myself because it's a TCP connection that I'm handling? I found that graph at the left is actually quite complicated, and although computers are fast, these packets have to go through all of this code one by one. And then when the first one is done, your cat video plays for a microsecond, and then the next packet comes in, and the CPU has to go all over again. And so actually your CPU hates it quite a lot. It's very slow. DPDK, Gerrit mentioned it before. It's a library originally written by Intel called the Data Plane Development Kit. And it runs in user space, and what we do here is we ask the kernel to unbind the network driver from the NIC and bind it to some user space driver instead, so that we can talk to the network card directly from a program running just in user space on the Linux kernel. I'm not going to talk that much about the DPDK stuff because Gerrit already handled that. Vector packet processing is an application that uses DPDK and also some other types of libraries to marshal traffic in from the wire using network cards and, say, DPDK poll mode drivers. And then it doesn't ask for one packet at a time like the Linux kernel typically would do. It will ask for many, say 200 or 256 packets at the same time. And what it constructs is very similar to the Linux kernel, except it's not linear. So it takes this vector, this list of packets, and it goes through this directed graph from DPDK input, Ethernet input, maybe it's an IPv4 packet, perhaps it's an MPLS packet. And because it goes through all these pieces of code together, all of these packets will amort all the CPU instruction and data caches that you have. And modern CPUs actually have quite significant caches in the CPU. And some CPUs, notably Intel ones, will also allow network cards or other PCI peripherals to send their data directly into the CPU's data cache, so we don't even need memory in this case. And these caches are much faster, like 10, 50, 100 times faster than main memory. And so this helps VPP to greatly accelerate packet forwarding in a data plane. So a quick intro to VPP, and perhaps I should ask by show of hands, how many people have ever played with vector packet processing? 1, 2, 3, 4, 5. All right, so 5 or so folks for folks watching at home. It's a pretty cool piece of kit, but one thing that you get is like you lose your interfaces from Linux, right? Because I just said they got unbound to their normal network driver and got rebound to a thing that allows VPP to use them, so they vanish from the Linux kernel. And I helped contribute a plugin to VPP that puts back these interfaces into the Linux kernel after VPP had removed them. And with the binary called VPP-CTL or VPP control, you can run this one-liner command called lcp create from a data plane interface called 100 gigabit Ethernet 400 and give it a host interface name called ICE0. And what happens next is this thing comes up in the Linux kernel again called ICE0, and you can manipulate it like any other interface normally would. Give it some IP addresses, perhaps create a sub-interface with VLAN tag 101, give it an MTU of 1500, bring it up, some IP addresses, some defaults, and you're off to the races pinging the internet. And what happens here is the Linux kernel will create this ICMP packet, send it into the VPP data plane, which will then route it into the internet. And as a packet comes back that is destined for an IP address that we've bound on the control plane, VPP knows to make a copy of it and stuff it back into this tunnel so the kernel sees it. And so in other words, just like in the Tofinos, all of the data plane traffic stays within VPP and you don't see it. And if you were to TCP dump, say this interface called ICE0, the only traffic you'll see is stuff that goes to the IP addresses you put on the interface. Everything that goes through the box remains invisible to you. So let's start by just running VPP. Some operational notes, how do we get there in the first place? The data plane is an API that does not have any configuration persistence whatsoever. It's not a fully fledged router, it's a data plane, and you're supposed to configure it. And so our position as VPP developers is, it is up to the user to create this control plane around configuring the data plane. So I contributed a tool called VPP config, which is a utility that takes a YAML file that describes what you would like the router's interfaces and things to look like, and then it constructs all the API calls that we need to bring the data plane into the same intent that the YAML file had given us. Right? So in other words, if you dump the running data plane configuration into a file like so, you may then edit this file, of course in Vim, not Emacs, and then add some interfaces, like a sub-interface here called 100 and 101, and this other interface here cross-connects to a sub-interface on the other side. Enfin, this configuration feels a little bit like a normal router configuration. What I can do then is plan a path from where I see the data plane to what we specified in the YAML file. And what will happen next is VPP config will construct all of the things that I need to do to change VPP to look like what I've just specified, right? And so the idea is that any config that you can specify in the YAML file towards any other config would be a safe transition as is computed by this VPP config tool. And it actually makes running a VPP router a whole lot easier than manually programming API calls into it. But after we've made a plan, we can also execute this plan by applying it into the data plane, which will take what I just showed in the previous slide and sort of stuff it into the data plane to move it towards whatever YAML file you specified. So that's the data plane side. But we also have a control plane side. We would like to run things like maybe OSPF or BGP or OSPF v3, things like that, VRRP, all this type of control plane things. And we could have implemented these as VPP plugins, but actually there's a lot of really good code already out there, and we all know that running a BGP router is quite difficult, but writing a BGP implementation is even more so. So instead of doing that, we'll use what's already out there. And in the case of IPNG, my pet network, I created a tool called Case, which is, I guess, also quite Afrikaans, but it's a Dutch name. And we read YAML files yet again that describe the higher level constructs, like which ISIS interfaces, or which OSPF, or which BGP, and which internet exchanges do we connect to, and so on. Put this in a YAML file, and then we create the configuration for the control plane. You can use many control planes, maybe FRR is a popular one. I myself use Bird. So what it looks like is this. There's an internet exchange in the Netherlands called the Fries IX. It's the Frisian internet exchange that I operate with a buddy of mine called Arend. And all you need to do is look up on the peering DB what IX ID this thing has. In our case, it's 3512. That's kind of all I need to know. There is an AS number present at this internet exchange. I know which internet exchange we're talking about. I can look up on peering DB all the other things, like the filters, the IP addresses, the max prefix limits, all of that stuff, right? So given only this very minimalistic configuration with some AS numbers there, it will compute everything I need to know based off of the awareness that I myself am a participant in that internet exchange, which I specify with a local addresses, which contain my IPv4 and IPv6 address at this FreeZix internet exchange. It calculates a bunch of things after querying the peering DB, so all the IP addresses and AS numbers and all that other stuff you'll find here just comes directly from the internet, making the config actually quite minimalistic. And it outputs one snippet for each internet exchange that this router is connected to. What I can do next is push this to the router, which will copy the configuration files into the running VPP instance, and then reload bird, which is just talking BGP and OSPF, just like any other Linux router would. And I can git commit this then to the Git repo. As I said before, the traffic that goes through the data plane is not seen by Linux. And so if I were to query how many packets or bytes an interface have seen, I will only see the control plane traffic. And so to add things to SNMP, I wrote a plugin that will talk to the data plane, query its numbers, because it obviously does know how many packets it sent in total, and then expose them into an SNMP endpoint so we can query with an NMS, like in my case, LibreNMS. And so I added some stuff as well to LibreNMS, so you can see the cute red doggy there at the top, which is the logo for VPP, and see that this router is casually doing 18 gigabits of traffic on a roughly $300 machine. That's old school. I'm a dinosaur, and so I still use SNMP, but most modern kids, I guess, will use Prometheus, which is a really cool tool as well. And I added an exporter, if you speak Prometheus, an exporter that will query the data plane, create all these metrics and offer them for scraping on the network, and then use Grafana to draw pretty graphs on everything that goes on in the data plane. And I'll get back to that in a second. So the VPP in production, tying it all together, the slides, my slides as well, are a little bit truncated, but there's a bunch of OSPF adjacencies. In this case, there's two backbone links, one that goes to Frankfurt and one that goes to Lille from this Amsterdam router, and then 3 local OSPF broadcasts. And if I look at the total route count, there's roughly 11 or so million routes in the RIB, and obviously the full table in the FIB. And one thing that is really cool about this approach, and your hardware vendor will typically not boast their numbers about this, is this guy reads a full table in about 7 seconds, and that includes programming the FIB. Because we don't need to write to TCAM and things like this. All of this is in memory, all of this is a user space process, and we can flush about 100,000 routes or so per second into the FIB, which is kind of nice. Okay, so performance. That's the main question. I already had Linux. Why would I use VPP, right? And the answer is because it's a whole lot faster than the Linux kernel would be. And I'd like to show you 2 parts. And the second part is why I'll run a little bit over on my time. First, I'll take 3 small machines, well, small, medium, and large machines, I guess, to show you the sort of the progression of throughput of VPP on a completely normal commodity PC that you could buy pretty much anywhere. And then I'll show you the sort of big kahuna computer that we purpose-built for this in a lab. I'll show you pictures of it as well. That is that famed Terabit router, the titular name of this presentation. But before I go there, I need to talk about another really cool DPDK app. It's called Cisco T-Rex. Again, open source. What it does is it generates traffic profiles and sends it through some device under test. It's kind of nice. It has a Python API, a bunch of clients for it. And it uses DPDK as well, so it's actually pretty quick. You do about 15 million packets per second on any one given core. And on a modern machine, you may have 64 or even 128 cores. So you can really blast a lot of traffic with this thing. You don't necessarily need an Ixia for that at all. All you need is a Linux PC. So how it works roughly is there's a YAML config that shows which PCI devices T-Rex should use. And let's say in this case I have two, and one of them is generating traffic from some source MAC address, which is light blue here. And it's sending traffic, right, to the other side, to this cloud, we call a device under test. And if the device under test successfully forwarded the packet, we can count it on the other side, right, on the second NIC. And then conversely, the purple NIC is sending traffic back through to the other side as well. And so really it's just a matter of counting chickens. Traffic that didn't make it through will not show up on the other side, obviously, and then we know that there was packet loss. So we can specify this config file with MAC addresses like I did here, or we can just take IP addresses and then T-Rex will simply use ARP resolution to figure out which Ethernet speaker to go send these traffic to. The startup is actually quite simple. There's a binary that you run as root so it can speak to DPDK, and then it opens an API port that you can connect to with this thing called Trex console. This one looks beautiful, I have to say. There are 3 machines that I tested here. As I said, a little bit of a smaller one, a medium one, and a somewhat larger one. The smaller ones come from Netgate, a US company that also ships VPP and a commercial product called Tensor. If you haven't yet, you should definitely check that out. And it's a simple Atom CPU. It's not very fast, it's very power efficient. It's not super expensive, but it's also not super fast, as we'll see. The middle ones here is what my ISP largely runs on. These are Supermicro 5018Ds. They're a Xeon medium-sized, like relatively old, but also pretty power-efficient CPU. They run maybe 30 watts or so TDP. And then the bottom one is an ASRock Ryzen that I built, that I do most of my development and load testing on. The thing is called Hippo because it is always hungry for packets. And Hippo has more interfaces. It has 2 100 gig interfaces and a bunch of 10 gig interfaces. So that's where I would like to try sort of and test more packet throughput with a bigger machine. The reason why I chose these 3 is every one of them is roughly twice as fast as the previous one. So when I do this load test with Cisco T-Rex, I have 2 methods to do this. Method 1 is to measure how much can a single CPU do. Like these machines typically have more CPUs. The Atom has 4, and maybe the Ryzen has 16 and 16 hyperthreads. And so how much can one of those do? And what I'll do is I'll tell VPP to use only 1 CPU, despite it being able to use more. And then I will send it traffic until it can forward no more. And then I know how much it does. And then I'll measure like how busy was it and where did the time go. And then method number 2 is more of the classic RFC 1544, where you ramp up traffic from 0 to 100% and figure out where is the traffic lost more than 0.1%, say. There's a bunch of interesting things that you can do with the second load test type, which is why it's a little bit more elaborate. And because T-Rex is driven by an API and there's a Python client for it, I contributed this T-Rex load tester that will just do as I mentioned before with a bunch of flags, which I'm not going to go in for lack of time. But there are a bunch of interesting profiles, and if you've ever seen router or switch vendors say that they can do up to 20 gigabits of traffic, then they typically mean they can do that with really big packets because there's less of them per second, and they're a little bit easier to switch. And so when we do this, we can say take 1,500 byte frames, which is standard Ethernet size, and that's actually a very simple load test to do. We can also do an iMix, which is a mixture of small, medium, and large packets, which is a little bit harder to do. And there's roughly 3 million per second in a 10 gig link. Or we can go all the way down to the smallest packet size that we're allowed to send, which is a 64 byte frame. Lower than that would be called a runt, and we're supposed to drop them. And so 64 bytes is the smallest we can get to. And that's about 14.88 million packets per second on a 10 gig link. And then there's 2 variants of this, also important for hardware vendors. Sometimes if you run only one flow, you'll find that the router or the VPP can only use 1 receive queue, 1 CPU thread, 1 outbound TX queue. So you're really limited in your expressivity in the data plane. Whereas if you use multiple flows, you can use receive side scaling, multiple receive queues, perhaps multiple CPU threads. And this is, by the way, not only for software data planes, this is also a fact in hardware data planes, where you may have lags or LACP signaled bundles that can saturate only one of the 5 links because there's only one big elephant flow going through them. So the T-Rex console kind of looks like this. It's a kind of nice textual interface, a TUI. And the legend here is on the top left here, you can see the network card info. In this case, like a 10 gig link that is transmitting some amount of traffic and how much time T-Rex is spending marshaling all this traffic in and out, which is about 16% or so. And then at number 2, you can see just bit counters, L1 and L2 traffic. Obviously, L2 traffic is a subset of L1 traffic because you need the framing overhead behind the Ethernet packet. And then on number 3, the traffic that came back the other side. And hopefully these two numbers line up. The amount of traffic we sent is the same as the amount we received. And then number 4 is insanely detailed packet counters, octet counters, things like that. So what you see here is about 19.1 gigs of traffic, which is 6.2 or so million packets per second, while T-Rex is using only 16% of its CPU. So now I'm going to compare these 3 machines that I mentioned before in method 1. So method 1 is take one CPU thread, one receive queue, and just saturate it until it goes no more. VPP has a nice statistics module inside of it that shows how many CPU cycles were spent doing this work. And when you start in, say, 1,000 packets per second, this is the top left on this atom, the smallest CPU that we have, every one packet that goes through the data plane takes about 4,943 CPU cycles. But if I move up to a higher rate, in this case 1 million packets per second, each individual packet all of a sudden takes only 620 CPU cycles. So that is an order of magnitude better than what we would have at a slower rate. So if I keep on ramping up further and further, I'll find that at 10 million packets per second, this small atom is using only 358 CPU cycles per packet. And it can do roughly 5 million packets per second for each core that it has. And it has 4 cores and 4 hyperthreads. So the Xeon is a little bit more modern and a little bit faster, also burns a little bit more energy. It's a 35 watt versus an 8 watt TDP. And there you see that at 1,000 packets per second, it's 2,037 or so cycles and 179, which means that it can do 10 million packets per second, which is almost double that. And then if you look at this Ryzen, which is a desktop CPU, it's not even that expensive these days. It's the same 178 CPU cycles per packet, except its clock goes all the way to like 5.2 gigahertz. So it does 22 million packets per second on one thread, and this CPU has 32 threads. So it actually does a lot of traffic. So now if I take method 2, I need to explain a little bit how this graph is formed. It does a load test that starts at 0 and then ramps up linearly to full line rate and then sees how much traffic comes out the other side. So what you see here is this graph, and the blue line represents what I'm sending from the load tester. And I know for sure that it can do full line rate. And so what I'll start off is like this 30 seconds of warm up where, I'll send some traffic like 1,000 packets per second, and I'm expecting that at least to work, and if not, something is wrong with the setup. Then I'll ramp up from 0 to 100% of line, and then I'll keep it there for 30 seconds to make sure that it can sustain this line rate. And there's 2 types of results you might see. Number 1 is this one. If you see the line flattening somewhere in the middle, and it did, say, 3 million packets per second, but not more than that, then, well, you'll see this flat line, right? So this thing did 35% of the line rate, and it could not forward more. There's one thing that's even worse than this, and that's that it goes from the 35% to 0, in which case maybe the router crashed. But in the case that it didn't crash, it'll do, say, 35%. And the more favorable outcome is that it just tracks all the way to completion and handles the traffic that I'm sending to it, and then I know that it can do 14.88 million packets per second, say. So first, let's look at the kernel. The kernel sucks at this. If you look closely at the bottom, you'll see a bunch of lines. They're really, really bad. So in the Xeon case or the Atom case, you can really only do maybe 600,000 packets per second on the Linux kernel, especially if you do only one flow, because then we get to use only one CPU. And the Ryzen is a little bit better, but still only 850,000 packets per second. And noting full line rate on one 10 gig port is 14.8 million packets per second, not thousands packets per second. It's not very good at all. So if I look first at this Atom, and I let it use one queue. We already established this before in method 1. It'll do about 5 million packets per second. But the cool thing about VPP and DPDK is they don't use threads that lock anything, so there's never contention. And the corollary is if you add more CPUs, you get more throughput. So if I add 2 queues, which is the orange line here in the middle, I'll do roughly double the traffic. You can see I went from 5.05 to like 10.10. It's exactly double. And if I add a 3rd queue, and I could add 8, because I have 8 threads, then I'll do 14.88 million, which is all I need for a full line rate 10 gig at 64 bytes. Right, so this tiny machine that runs maybe 8 watts TDP can do at least full line rate 10 gig. If I take the Xeon, 1 thread will do 10 million packets per second, and 2 threads, well, obviously would do 20, right? But I only have 14.88, and so 2 or 3 threads doesn't matter. It'll forward all of this with 2 CPU threads only. And the Ryzen doesn't care, right? It can do 22 million packets per second on 1 CPU thread, and so just 1 can saturate. It doesn't matter if I use 1, 2, and 3. It's kind of nice. But if I tweak it a little bit and only use 1 flow, then no matter how many receive queues and CPU threads I have, well, VPP and RSS and the network card can really only marshal it into 1 receive queue, which means only 1 CPU thread could be used. So it doesn't matter if I use 1, 2, or 3 CPU threads, 1, 2, or 3 receive queues. There will only be 1 active at any given time, which is why under the magnifying glass, you'll see it doesn't matter if I used 1, 2, or 3. And so the small machine has some benefits. It's cheaper, it's way cheaper on power, but it's also weaker per individual thread. So you cannot do load, line rate load with 1 CPU thread only. And of course, the Xeon that we use at IPNG will do 10 million packets per second, and the Ryzen would, again, not care, right, for this. So what if I took a really, really big computer? I had a conversation last year on Twitter, when I was still on Twitter, about the claim that I could do 1 billion packets per second with a computer, with a PC. Now, granted, these are no longer normal PCs. They're very specialist builds. You need to find the right motherboard, the right CPUs, flash firmware, micro firmware into the CPUs, do BIOS updates, like all of that stuff. I have a buddy called Vlad, and Vlad is actually really good at that. So we went and built this machine, and then we also needed some big machines to generate the load, right, obviously. So we built 3 of these machines. I want to show you the setup here. There's this load generator on left and right-hand side, and they're running T-Rex. And they're running 2 of these machines just with Debian, and they have Intel workstation CPUs. These all run with PCI 5, which is a very fast PCI spec, very modern. And they run these network cards from Mellanox, today it's called NVIDIA, that have these ConnectX series. So we ran some ConnectX 5, some ConnectX 6, and some 7s. Basically anything we could find on eBay, because these things are not always easy to find. So that's on the left and right-hand side. And then in the middle, there is this one machine, we call it VPP bench, and it is trying to saturate all of the load that comes in from both load testers at the same time and sending it all back, right? Just as I described before, but a little bit more on steroids. And then I have Clyde from XKCD at the top there, and he is standing on this controller that's just ramping up and down traffic on both of the load testers, all the while using Prometheus to measure how much we're actually receiving back on the other side. And so the device under test, I put the specs in there. It's a dual Intel Xeon. It's a pretty fast machine. But of course, you need to, right? If you're doing 100 gigs, 200 gigs, 400 gigs, you definitely need to start beefing up the machine. What I like about it is that VPP will go all the way down to a tiny computer and all the way up to a gargantuan computer like this one. So method 1 here, again, the single thread saturation, where I turned off all the CPU threads except for 1, and then I send as much traffic through the machine as I can. Here we see for each network card, there's 2 100 gig cards and 2 200 gig cards that we do roughly 264 million packets per second in this same mode that I showed before on the small machines. Except there it was 6 million, and here it is 264 million packets per second. It's actually quite a bit. And then I also wanted to show a little bit of the difference between the types of forwarding you could do. And caveat, the previous table that kind of looked the same with the 3 machines in it, it was talking about IPv4 forwarding only. So this is a slightly different table, just for the record. Here I'm testing 4 different types of forwarding on this big computer. So the cheapest for me to do is L2 cross connect, right? Where you just take the Ethernet frame in on one port and copy it back out on the other. There's no route lookups, there's nothing. It's actually a very simple thing to do. And then IPv4, IPv6 is a little bit more expensive, mostly because the fib is a little bit more complicated, and MPLS as well for good measure. And here I see that one CPU thread can do 32.8 million packets per second, which is almost double, not quite, 1.5x that of the Ryzen that I tested before. And again, the amount of CPU cycles that I take for each individual packet going through the data plane greatly decreases when load increases, which is kind of counterintuitive. But if you think about it, these CPUs have a lot of cache in them, and they amort all of this cache if you take a vector of 200 packets and ask it to do the same thing 200 times. It just gets way more efficient as it does things a lot of times in a row. So even the slowest thing I can do, which is MPLS forwarding, allows me still 19.4 million packets per second on one CPU thread. And this workstation had 256 CPU cores. So first, despite the slide being somewhat overlaid here, we ramped up a load test and looked at Prometheus. And you can see here all these bars. Maybe I have a laser pointer somewhere here. Yes. This first bar here just ramps up the first port from 0 to 100% of its line. And then the second one, the blue one, and then the third one, this orange one. And then you can see this dotted line here in blue, and that's just the lump sum total, which is on the other axis on the right-hand side. And the horizontal bar is the goal here. I wanted to do a terabit. And you can see around that point, we reached a terabit, and then we were not done yet. Apparently, the machine wanted a little bit more. And so the load test saturated itself at 1,250 gigabits per second on this machine. By the way, these are large packets, so they're actually relatively easy to do. And the bottleneck here is not the CPU at all. It is the PCI bus. It is trying to send as much data in and back out through the PCI bus, and the CPU is actually relatively underutilized because it didn't have that much work to do. The harder thing to do is forward small packets. Let's take a look at that. Well, we did not reach 1 billion packets per second, which is a little bit upsetting, but we got very close at 923 million packets per second. This was a load test in December, in November of last year. My buddy Vlad, in the meantime, on the same computer, has tweaked some more, and he reached 1 billion packets per second. But that'll be a presentation for another day. So at 1122, we did 100 million packets per second, which is actually quite simple, relatively speaking, for this computer. And at 1242, we topped out at 923 million packets per second. Again, a completely open source, completely functional router with BGP, OSPF in the works. So with that, I had one more picture, and surprisingly, I'm coming in under time. I don't know what happened. And that is the picture of the setup in my basement, taking 1.8 kilowatts of energy, turning them into heat as they were pumping all of this traffic through these DACs. The left and right-hand machine are the two load testers, and the middle one is the VPP bench that is routing a good terabit of traffic, or almost 1 billion packets per second, all the way up and all the way down. It was so awesome that the screen broke. There you go. So with that, I'm out of material, and ironically have a couple more minutes. And for the record, for Switzerland, it is now 15:59, which means I'm a minute ahead of schedule for the whiskey.
Any questions? Just when is he coming to Cape Town? Set it up, we have set it up.
Yeah, it's true. When am I coming to Cape Town? In 2 years, I think there's a Zenock there.
Any other questions?
I'll be around. By the way, I took some pins with me. It's total, like, not a sponsor. However, I took some pins with me, and if you would like one of them, come hit me up or just grab them from the table there. They have an RFID, and every month you have a different technical article from IPNG.
Right. Thank you very much.
You're welcome.
Right, so we have gotten to the end of today's technical talks, but we have some more non-technical talks that's going to happen over the whiskey. But first,